Brilliant. Thank you very much, Josie. So yeah, welcome to the Applied Catalysis Group UK Catalysis Hub webinar. Today focusing on the theme of challenges in catalysis for pharmaceuticals and fine chemicals. So I'll hand over to Amanda to introduce the first speakers.
Hello everyone, and welcome. So just jumping straight right in, our first speaker today is going to be Nessa Carson from Syngenta. So Nessa started her career in the pharmaceutical industry after training in organic chemistry and catalysis. She's since then worked on high throughput automation, both in Eli Lilly as well as Pfizer, and she's now working at Syngenta. And today she's going to talk to us about data management behind high throughput experimentation and automation. So over to you, Nessa.
Oh, thank you very much, Amanda. Okay, let me try and... Is that looking good?
Yes.
Oh, brilliant, thank you. Hopefully I will be able to keep sharing this. My connection's been a little bit funny today, but please shout and wave your hands if it starts to go a little bit south. But yeah, I'd really like to talk about data management in high throughput experimentation today. It's a bit of a high level talk. I don't have specific instances of catalysis that I'm going to talk about. But I think this will be useful for people doing or working with those who do high throughput experimentation or HTA, or those who want to, which is more and more people these days. So I'm not going to delay too much of an introduction now. I'm going to get right into it, especially as we also have David Sale later, who will be able to give us some useful background on what Syngenta is doing as a whole. Yeah, okay, there we go. So going straight into it, then at the root of agrochemical discovery and pharmaceutical discovery, I'm sure many people have seen cycles like this before. DSTA cycle, design, synthesize, test, analyze. So this kind of cycle is probably quite familiar. It's about knowing what to make next in the context of discovering new small molecules, agrochemicals or pharmaceuticals. But within that step of synthesizing before we're testing these for biological activity and then analyzing those results, we also have a smaller cycle, which here we're calling a DEA cycle, so design, execute, analyze. And basically this is at the heart of reaction optimization. So we're starting off by, I guess, designing our reaction conditions. So we've designed our molecule now we know what to make, but we need to figure out how to make it. So we're designing our reaction conditions. We're trying it out. We're analyzing what happened in that reaction, and if we've decided that it's not good enough to give us enough material to go on to biological testing, we're going back again in an iterative fashion, which my cat is really excited about right now. He really wants to join in. So let me just move on. So basically, what we end up with is that we're generating data in reaction optimization. And we have to kind of find a way to deal with all that data. So this slide has a lot on it. I'll just kind of talk through the basics of why this slide has a lot on it. And basically, I guess we're thinking about how to use those data to accelerate going through the whole DSTA cycle. Actually, what I should say is that high throughput experimentation, I'm based in discovery mostly at the moment, but this is useful at all stages. It's particularly useful in process research. And I guess one of the really nice things about working with high throughput experimentation is that quite often you can bridge the gaps between the two, which means you get to learn about the two and kind of figure out how everything fits in to each other within the industry. I think that's one of the really awesome kind of perks of the job. But what's going on this slide, I guess, is that I suppose we want to figure out both what to make, and then I guess we need to be able to feed that back into something so that a computer can understand it. And we're going to need a computer to understand it to be able to tell us more about what our next reaction is going to be. So I think this slide is built with the idea of synthesizing compound libraries in mind. But it works just as well for reaction optimization. So whether you're thinking about the exact molecule you're making, or you're thinking about the conditions that you're using to make a specific molecule that you've already designed, the same principles with data really apply here. So basically, I guess one of the big points of this is that when we're dealing with automation, because I can work on so many reactions at once, and I'll talk about that in a minute, we need a good way to store all these data. We need to be able to find them later, which is a really big deal sometimes. It's difficult to find your data if they're not labeled in a meaningful way. So the reaction data lake is a really big part of this, and I guess that's where all my reaction data are going to end up. And then when we go around that DEA cycle the next time, we'll have all those data from the past that are ready to inform us about what we do next, hopefully with the help of, in the future, right, of artificial intelligence, machine learning, all those kind of things as they develop alongside the chemistry. So, okay, that was all kind of very high level and also reasonably complicated. So I'll show you how we actually do this practically in the lab. So in my lab, then the purpose really is helping projects to explore and improve reaction conditions efficiently. And we're doing this by using medium to high throughput experimentation and automation to screen different reaction conditions. So I'll be using solid and liquid dosing robots. Here are some of them here. These are stock photos, but they are models of the same robots that I'm using. And we'll be doing small scale parallel reactions. So I typically would use one of these 96 well plates. And I guess most of the time I would probably only be making 1 or 2 products across that entire plate. So these are really the bread and butter of high throughput chemists, as many of you will have seen before. And yeah, I guess that's the sort of everyday experiment. I would just run 96 iterations of the same thing with different conditions in there to explore 96 different hypotheses. And then also a really big part of the job is analysis, quantification, and data management. So we do this for many reasons. It's definitely not just about getting yield up, although that is definitely a bit of a stereotype of discovery chemistry. But even at these early stages, we're interested in improving sustainability. We're interested in improving cost of goods, cost of the materials used, so that we can scale up as quickly as possible. And scale in the agrochemical industry is huge, right? We're going to ton scale pretty much as soon as we start process chemistry. So being able to work on these even at the early stages, yeah, it's definitely really important to us. One thing that we think is important is the third point here, getting quantified results that map to the reaction conditions. And I think I mean 2 things really by that. So we want the data to be quantified so that they're understandable by the computer that's looking at our model and deciding what to do next. But also when we're storing data in our data lake, I've seen big dumps of data, and they are, yeah, they definitely have issues with being able to find what you want in there. So it's really important that our data are labeled, preferably automatically, because the chemist running the data doesn't really have time to be able to add in tags to every single experiment. And let's remember that in a high throughput lab, I guess a typical week for me in the past has been like 1,000 reactions per week. So I definitely don't want to be doing all that manually, right? And that will help us to generate standardized data. So I'll just talk really quickly about, I guess I kind of want to sell high throughput chemistry really quickly in case anyone's not quite convinced. And I quite often show this paper. This isn't my paper, this is by GSK, but I really love it. So I'm not showing what reaction this is here because it almost kind of doesn't matter. The point is, we've got our 16 different phosphine ligands. It's a cross-coupling reaction, right? But we've got our 16 different phosphines. We're trying one base and one solvent. And we are just testing these 16 different ligands. We're not varying the base and solvent yet. And we see that xanthos is the best. Moving on, these researchers then thought, okay, so we like xanthos. Xanthos is really good. Now we're going to try 2 different bases, potassium carbonate and potassium acetate. We're also going to try these in toluene. And we're going to run those 6 combinations all with xanthos. And we see that still, xanthos, okay, we know xanthos is the best ligand, and it looks like disopropylethylamine is still the best base, and it looks like acetonitrile is the best or the better solvent. But here's a line from this paper that is really important. Classical screening gives a local maximum, not a fully optimized system. So this is the kind of screening that, I mean, to be honest, I did this in grad school all the time. You still see this in papers constantly. We optimize on one factor at a time. And that's maybe okay. Maybe that will get you to the point where you want to be. Particularly in catalysis, I would say it is dangerous. If you really want to reach the optimum of your system, it's probably not the way to go. And I'll show you what happened when the researchers tested every single combination of these variables all at the same time. So we've still got our 16 ligands, our 2 solvents and our 3 bases. And now we're looking at all of these results. And actually there are 8 better sets of conditions compared to this one in the corner that we saw before. Across here, there are 8 better sets of results. And the one that actually works out being the best with 99% yield compared to 81 has a completely different set of conditions than what we earlier thought was going to be the best. And I guess this is the thing with catalysis. So I think this was just happened to be for a carbonylative verification to form an ester. And particularly with reactions like that, so Buchwald-Hartwig reactions especially, I always cite them because they're so troublesome, and that's why we get so many of them in high throughput chemistry. But yeah, the mechanism is always changing. The slow step is always changing. You're getting off cycle effects, and these are so complicated that it's going to be difficult to optimize your reaction with one variable at a time. I guess I should also say, actually, of course, you can maybe cut down the number of experiments you do with statistical techniques like design of experiments. In many cases, it's actually faster to run a full factorial experiment, which is every combination of each one of those levels of the variables. But what I tend to get out of my experiments looks like this. So it's probably complicated. The first time you see it, people adapt to these really quickly, basically immediately, because I like to use the same format every time so people understand what's going on. So I guess I ran my design in a similar way to that last experiment we saw. This is a different experiment, but it looks kind of similar in its design. And then I've got a color that represents each of the different products. So I guess green is good here. So green here is my desired product. So what we want is a full green circle. The size of the circle also matters. So the bigger it is, the cleaner the reaction, essentially. So we want a big green circle there. And I can just very easily see what's going on across the entire plate here. So from a data point of view, this is very human interpretable, especially with that small amount of familiarity that it takes. And there's a lot lying behind it. So straight away, I think even if you've never seen a plot like this before, you can pretty much immediately go, oh yeah, it looks like AmPhos is really good. It looks like sodium T-butoxide is pretty nice. Let's stay away from Ad-Bretphos and T-butyl-Bretphos in this particular case. So short term, this is great, this kind of image. We need this experiment to be human readable so we can generate conclusions. In the long term, we're also going to need our data to be machine readable. So yeah, we are generating a lot of data here. We need to feed them back into that chemoinformatics cycle so that the next time we do run a similar experiment, we know about it, we know about what's happened here, and we can use those data to our full capabilities. You know, it's kind of interesting. I was at the RSC artificial intelligence in chemistry meeting yesterday, and they really made this point repeatedly in the talks and in a panel discussion at the end, that the people who are running chemoinformatics and computational modeling, they're worried about high throughput data that's being lost at the moment. And I think this is generally across companies. We're maybe not exploiting the data to its absolute optimum, and that means that they can't use it effectively in their models. And the problem is things like finding the data, things like organizing the data. So I was never quite sure whether I was even doing big data in the first place. And I talked to my friend who's a biomedical scientist, my friend Avi Roy. He has a lot of expertise in epidemiology. He knows about big data. He's dealing with medical data, patient data, that kind of thing. But yeah, I think I always had a bit of sort of imposter syndrome when I was talking about big data, because, you know, I'm running 1,000 samples a week, I guess, 100 samples in a single data set. And I didn't think that was really big enough. But Avi says, I don't think about big data in terms of number of data points. Big data is high dimensionality, high volume data. And looking through what we're doing, I mean, this is a single LCMS trace. So in high throughput, we're getting 100 of these per experiment. And I mean, this is huge. This is 9.71 megs, depending on which vendor makes your LCMS, basically, in every single data file here. So in total, you're generating a lot here. So you've got for your diode array, I guess you in my particular case for a sort of standard LCMS experiment, I have this entire 3D plot of data points that have been generated. So we've got 20 per second on the diode array. We've got 10 per second on the ELSD. We've got mass spec that's going at 5 hertz in both the positive and the negative. If you put these together, that's an awful lot, right? And we end up generating a gigabyte of data per 96 sample plate. I think one of the really critical things here, actually, is that from a big data perspective, when I was talking to my friend Avi, he was really surprised to know that we're generating this much data, and it's so much that the computer can't really understand it by itself. We need human intervention by an expert chemist to distill this down into something meaningful, like 55% yield, or like the proto deborylated product is the major side product. So we have to think about storing both these raw data and the arguably more important the distilled down understood data by the actual chemist. So yeah, I like including an image like this. This is quite a recent one. This is a real experiment that I ran in the lab, and this was actually the best results I got in that particular experiment. It wasn't a very big screen. but it was looking good. And this dark blue peak right here is the product that I wanted, and this is what we went with, and this is what we fished out and submitted for biological testing. The point I'm sort of trying to make here is that this was the best yield, and in this case we liked it, but quite often you might show this trace to a chemist, and they would say, this is terrible, this is not what I want at all. So you're also optimizing for things like profile and chromatographic purification. You might be optimizing for selectivity, you might be optimizing for cost reagents, toxicity, select criteria, sustainability, or many combinations of these. So understandable by computer actually means a lot of things. It requires standardization, and being able to automate in whatever way, generating the metadata and the important parts that are understood by the chemist are really great news for us. So I guess I'm quickly gonna get to the end of this. I think the future of high throughput synthesis data is going to be really important. It's important now, and it's going to increase in its importance moving on, because this is how we're generating our own understanding of chemical reactions for the future. We need to have these large data sets, because data sets at the moment, according to the chemoinformaticists I know, are generally not big enough to generate that computational understanding of what happened next, how to improve, how to accelerate these DSTA cycles and get better as time moves on, which seems to be what every company is really pushing to do right now. So this is what we need: the fair data principle, findable, accessible, interoperable, reusable data. It's arguably the most important thing that we can do with our data. So as a high throughput chemist, yeah, you don't need to code, but it's important to, I guess, have some understanding of the data management within chemistry. And every single high throughput chemist, whether that's you or the people you're working with, needs to think about data management and use sense. Otherwise, we are wasting the data that we're generating. If we can just use it for one experiment, why not use it for our future experiments too? And just to kind of summarize what high throughput chemists are always saying whenever we get together at the moment, the things we're looking for in the future to make catalysis better and to make chemistry better are not really chemistry in a way. We're looking for open source software, standardized operating platforms, and that's so that we can understand data and so that all the data can come together and talk to each other in a way that makes sense to chemists and makes sense to computers. Part of that can be Internet of Things for reliable data collection. It can be reproducible workflows. And eventually, the end goal, the big goals are artificial intelligence, machine learning, self-optimizing reactions. So I think I'm coming to the end of my talk here, but I'd really just quickly like to acknowledge all my colleagues and my whole team at Syngenta, and I'm very happy to take any questions. Thanks very much.
Thanks a lot for that talk, Nessa. So an excellent overview of data management and some of the potential pitfalls or opportunities within it going forwards. So I'd like to open the floor to questions. If anyone has a question, please write it in the Q&A. Whilst I think the first questions have been written in, I just had a, I guess, comment / question. So I guess one of the things that people say about using machine learning is that in the past, you have a lot of positive results. So you only know what works because people only report what works. Do you see high throughput experimentation and this sort of work actually helping to kind of get some of those bad results?
Yes, absolutely. And we do get the bad results. We really do. Having said that, yeah, I think it's a bit of a constant battle, really. You know, when I'm designing the high throughput screen, I've never done an experiment that hasn't been bespoke to that transformation. So I don't run things like standardized plates. I know some people do, and that could be a really great way to help with this, to explore chemical space a little bit better. Having said that, yeah, I don't personally do that. I design all of my experiments with what, to me, with my knowledge, is the best chance of getting a great result coming out. And that means that, yeah, I might be missing out on some of those areas of chemical space and some of those some of those negative results that are genuinely extremely useful and valued by machine learning. That's absolutely for sure.
Okay, thanks a lot. Yeah, we've got a couple of questions coming through the chat. So Abraham asks, what is the model, ontology, or vocabulary you use for annotating data?
Okay, good question. Probably slightly out of my expertise. I guess what I personally am doing, I like to work in a sort of prototype model. So it can be difficult quite often to get resources of like IT type resources, data science resources for a project before you've been able to prove it. So I like to kind of prototype things myself. And then once I've been able to prove it, then, maybe I'll be able to get some resource from people who actually know what they're doing instead of just me playing in Python. So yeah, I guess when I do a design, I really want the screen design to be attached to my results and to be fed in. So I guess all I'm doing is using Python to tell the LCMS what's in the file, basically. That's literally all I'm doing right now. Having said that, yeah, the value is really great because when I'm trying to visualize at the end in Spotfire, it's all right there. I don't need to mess with anything. I design it once. I never have to repeat anything. I hate repeating data entry because the chance of it going wrong is really very high.
Yeah, I guess that's often where you get mistakes, right?
Absolutely.
So there was another short question, which was, what's the meaning of the circle size? I see there are differences in the circle size in your experiment, so I guess that goes back to your plots that you had. Yep,
sorry, I should have explained that a little bit better. Yes, that's just something that I really like doing. Basically, the circles here represent how clean the reaction is. So if I had 100% of my desired product, it would be a big green circle. In this case, there are clearly a lot of side products that I've not defined.
Okay, great. And we've got a question from Guy Lloyd James here, which goes back to future-proofing data storage. So how do we future-proof data storage to ensure it's accessible? He gives an example. I have lots of old PowerPoints that can no longer be read by current software. Similarly, zip drives that went out of use. Yeah, we've all had things which have been run on a piece of equipment and that software's died or that piece of equipment's died and we can't look at it.
Yeah, absolutely, definitely a big issue. I suppose one of the really important things is standardization, which a lot of people are talking more and more about right now. So being able to distill anything down to its simplest, most understandable elements, I suppose, is probably an important part of this, I would say. So yeah, here then I guess we can see a shiny data visualization, but actually what's happening is it's just some labeled numbers stored in, well, in this case, it's an Excel file. I use Excel because a lot of robots use Excel. My team uses Excel. People can read it, that kind of thing. Yeah, it's completely true. I do think things like cloud storage, probably in 100 years that will be completely different. But the fact that we can all access this from wherever we are, I think is extremely helpful. Another one of these problems is when someone leaves or moves on or can't access their data anymore and the data is lost with that person. Hopefully we're all trying to move away from that right now.
Do you feel that industry is managing to move away from that and does have things in place that mean you don't lose data when someone leaves?
I think we're getting there. I guess that's hopefully one of the big advantages to moving to this model where we're using data lakes and being able to think of experiments in terms of what we've done in the past. Yeah, so I guess when someone moves on, you're losing their knowledge, right? But hopefully you're not also losing their data. If a computer can help with that, then that's a great thing.
Okay, and lastly, we have one last question who's asking on the question of designing your experiments, are you doing this only on the basis of computational or using some experimental?
Yeah, that's a really good point. I like things to be a mixture. I have been bitten in the past, actually more than once, by something that was designed by a computer, and if you just take a computer's word for it, that is a very, very dangerous place to be in my opinion and in my experience. So yeah, I think we're moving towards more computational design. I don't for a second believe that we should be removing chemists from this equation. The two interesting parts of high-throughput experimentation are the design and the analysis. Yeah, there are some really great ways to explore chemical space that I think we should be using computers for, because humans are biased. Humans rely a lot on what they've done before, what they've seen before, what their PhD supervisor liked to do, for example. Yeah, it would be fantastic for it to continue to be a mixture.
Cool, great. Well, thanks again, Nessa, for that talk. And we'll now move on to our next speaker.